You hear the phrase quantum computer and it can sound like a magical black box. But if you strip away the hype, a quantum computer is still a machine built by people inside laboratories using real hardware, real control systems, and real engineering trade-offs. The difference is that it does not use ordinary bits as its core building block. It uses quantum systems called qubits that follow the rules of quantum physics. That means to understand how quantum computers are built, you need to understand both the physics and the engineering. You are not just building a faster laptop. You are building a machine that must prepare, control, protect, and measure extremely delicate quantum states. This is why quantum computing is one of the hardest technology challenges of your time. It sits at the intersection of physics, material science, cryogenics, lasers, microwave engineering, software, error correction, and advanced mathematics. Quantum computers are real machines built from delicate quantum hardware, not magical black boxes. A classical computer is built from billions of transistors that act like switches. Each switch represents a bit that is either 0 or 1. A quantum computer is different because its core unit, the qubit, can exist in a quantum state that allows a richer form of information than a simple on-or-off switch. That is why quantum computers are not built by simply shrinking ordinary chips. They are built by taking physical systems that naturally behave according to quantum physics and turning them into controllable computing devices. This is also why there is no single standard design yet. Some companies use superconducting circuits cooled to incredibly low temperatures. Some use trapped ions controlled by lasers. Some use neutral atoms held in place by light. Some are pursuing topological qubits. Every one of these approaches is trying to solve the same problem. How do you create qubits that are controllable, stable, scalable, and accurate enough to do useful computation? Quantum computers are built differently because qubits obey quantum physics, not ordinary digital logic. The first major design decision in a quantum computer is choosing the physical system that will act as the qubit. This is the heart of the machine. A qubit must be something you can prepare in a known state, manipulate with precision, keep isolated from noise, entangle with other qubits, and finally measure. That sounds simple in one sentence, but it is brutally hard in practice. This is why different quantum companies emphasize different strengths. Superconducting qubits are attractive because they can be fabricated using chip-style manufacturing and controlled very quickly. Trapedion systems are attractive because ions are naturally identical and can deliver high-quality operations. Neutral atom systems are attractive because they appear highly scalable and can be arranged into large arrays using lasers. Microsoft is pursuing topological qubits because the long-term goal is to create qubits with stronger built-in protection against errors. Every quantum computer begins with one key choice. What physical system will become the qubit? One of the best-known quantum computer designs uses superconducting circuits. In this model, engineers fabricate tiny electrical circuits on chips using materials that become superconducting at extremely low temperatures. These circuits are designed so that they behave like artificial atoms, meaning they have discrete energy states that can be used as qubits. Microwave pulses push these qubits into the states needed for computation. But the chip itself is only one part of the story. The chip has to sit inside a dilution refrigerator that cools it to a tiny fraction of a degree above absolute zero. The reason is simple. Heat is the enemy of quantum behavior. If the environment is too noisy, the qubit loses the fragile state you are trying to preserve. That is why superconducting systems come wrapped inside ultra-cold, highly engineered structures filled with control wiring, shielding, and electronics. Companies such as IBM and Google have advanced strongly in this direction. Superconducting quantum computers are built like ultra-cold chip systems, where fragile qubits are controlled with microwave signals. A very different design uses trapped ions. In this model, the qubits are individual charged atoms suspended in electromagnetic fields inside a vacuum system. Lasers are used to cool, prepare, control, and read these ions. This approach may look less like a normal computer chip and more like a precision physics experiment, because in many ways that is exactly what it is. The strength of trapped ion systems is that the ions themselves are naturally identical, which is very attractive for building high-quality qubits. The challenge is engineering at scale. You need precision optics, stable vacuum conditions, tight laser control, and careful orchestration of many moving pieces. Quantinuum and IonQ are both major names in this area, though they use different architectures and strategies. Trapped ion quantum computers use suspended atoms and laser control instead of chip-like switching. Another important design uses neutral atoms. Here, individual atoms are trapped and arranged using finely controlled laser beams. Because the atoms are neutral rather than charged, they can potentially be packed into large arrays more easily. The qubits are typically encoded in internal atomic states, and lasers are again used for control and measurement. This approach is exciting because it offers a strong story around scalability. Companies such as Atom Computing emphasize large qubit arrays and the advantages of optically trapped neutral atoms, including a path to scale through light-based control rather than dense electrical wiring. That does not mean the engineering is easy. It means the scaling model looks promising if fidelity and error correction continue to improve. Neutral atom systems aim to scale quantum computing by arranging many laser-controlled atoms into large arrays. Topological quantum computing is one of the most ambitious approaches because it aims to build qubits that are more naturally protected from errors. Instead of trying only to correct fragile qubits after the fact, this approach tries to encode information in a way that is inherently more robust. That is the promise that has kept the field interested for so long. Microsoft's Majorana 1 announcement in February 2025 put this approach back into the spotlight. Microsoft described Majorana 1 as the first quantum processor powered by a topological core and said it was designed with a path towards scaling to 1 million qubits on a single chip. This is a very different path from the superconducting and trapped ion approaches, and it remains one of the most closely watched efforts in the industry. Topological quantum computing tries to make qubits safer by building error resistance into the hardware itself. When people first hear about quantum computers, they often focus only on the qubits. But a real quantum computer is much more than qubits. It is an entire stack of support systems built to keep those qubits alive and useful. In superconducting systems, that means cryogenic refrigerators, ultra-low noise electronics, shielding, and precisely timed microwave control. In ion and neutral atom systems, that means vacuum chambers, lasers, optics, stabilization systems, and readout hardware. This is one reason scaling is so hard. Adding more qubits is not just a matter of placing more units on a diagram. You also have to scale the cooling, calibration, control signals, readout, wiring, software orchestration, and error management. The hidden machinery is often the real story. The visible qubits are only the tip of the system. The hidden engineering stack is what keeps quantum hardware working. Once you have qubits, you need to operate on them. In classical computing, gates manipulate bits. In quantum computing, quantum gates manipulate qubits by changing their quantum states in carefully controlled ways. These gates are created using physical control actions such as microwave pulses for superconducting systems and laser pulses for ion and atom systems. Some gates affect one qubit, others entangle multiple qubits. These multi-qubit operations are especially important because entanglement is one of the main reasons quantum computing can outperform classical approaches for certain problems. But multi-qubit gates are also where errors become painful. That is why hardware teams constantly push to improve gate fidelity, connectivity, and repeatability. Quantum gates are physical control actions that push qubits through carefully designed state changes. If you want to understand why building a quantum computer is hard, come back to one word: errors. Qubits are fragile. They interact with their environment. They lose coherence. Control pulses are imperfect. Measurements are noisy. Crosstalk appears. Materials defects matter. This is not a side problem. It is the central problem. That is why the industry no longer talks only about qubit count. More qubits are useful only if those qubits are good enough to support meaningful computation. This is also why the conversation has shifted toward logical qubits, fidelity, gate depth, connectivity, and error correction. A smaller number of high-quality logical qubits can matter more than a larger number of weak physical qubits. The biggest barrier in quantum computing is not adding qubits. It is controlling errors well enough to trust them. Quantum error correction is the method used to protect quantum information by encoding one logical qubit across multiple physical qubits. In simple terms, instead of trusting one fragile qubit to hold critical information, you spread that information across a carefully designed group of qubits so that errors can be detected and corrected along the way. This is essential if quantum computers are ever going to become truly fault tolerant. This is where some of the biggest recent progress has happened. Google's Willow results were notable because Google said the chip showed error rates falling exponentially as larger encoded arrays were used. IBM said in late 2025 that its Loon processor demonstrated the processor components needed for fault-tolerant quantum computing. Quantinuum and Microsoft have also highlighted logical qubit progress. These are meaningful signs that the field is moving from "can we control qubits" toward "can we protect them reliably enough to scale?" Quantum error correction is the bridge between fragile lab qubits and reliable large-scale quantum computing. A quantum computer is not useful without software. You need compilers, orchestration systems, calibration routines, error mitigation tools, and classical computers to help manage the whole process. In fact, for the foreseeable future, quantum computing is likely to be hybrid. That means the quantum processor does part of the work while classical high-performance computing does the rest. This is one of the biggest lessons from recent progress. IBM's roadmap emphasizes quantum plus high-performance computing, including better mitigation tools and dynamic circuits. Quantinuum has also described hybrid workflows that link a classical supercomputing with trapped-ion quantum systems for scientific computation. Even when quantum hardware is not yet fully fault-tolerant, hybrid workflows allow classical and quantum systems to work together in useful ways. Quantum computing is becoming a hybrid stack where classical systems and quantum hardware work together. Google's recent progress has centered on Willow and the move from benchmark-style claims toward more verifiable and application-oriented demonstrations. In December 2024, Google said Willow showed exponential error reduction as larger encoded systems were used and also completed a benchmark computation in under 5 minutes that Google said would take a supercomputer an unimaginably longer time. That was a strong signal around error correction and benchmark performance. Then in October 2025, Google announced Quantum Echoes, calling it the first ever algorithm to achieve verifiable quantum advantage on hardware. Google said the Willow system ran the algorithm 13,000 times faster than the best classical algorithm it compared against, and framed the result as a step toward real-world applications, because the method connects to physical systems such as molecules and materials. Google's recent progress is about moving from hard benchmarks toward better error correction and more verifiable quantum advantage. IBM's latest progress has been framed around a structured roadmap that connects hardware, software, error mitigation, and fault tolerance. In its 2025 roadmap, IBM said Nighthawk would be a higher connectivity processor built to execute more complex circuits and support exploration of quantum advantage alongside high-performance computing. In November 2025, IBM said Nighthawk would offer 120 qubits with higher connectivity, while Loon demonstrated the hardware elements needed for fault-tolerant quantum computing. IBM also highlighted new software improvements and high-performance computing-powered error mitigation advances. What makes IBM important in this race is not just the hardware, it is the system-level story. IBM is clearly telling the market that useful quantum computing will come from integrated progress across fabrication, chip architecture, couplers, error correction, software, and hybrid workflows. IBM's progress is strongest when you look at the full system: processors, software, mitigation, and fault-tolerant roadmap together. Microsoft's latest progress has focused on topological quantum computing and on integrating quantum error correction and hybrid infrastructure into a longer-term supercomputer vision. In February 2025, Microsoft announced Majorana 1, describing it as the first quantum processor powered by a topological core and saying it was designed with a path to 1,000,000 qubits on a chip. That is a bold claim and reflects Microsoft's very different hardware philosophy. At the same time, Microsoft has also been involved in logical qubit progress through collaboration with Quantinuum and in hybrid systems, thinking through Azure Quantum. Its roadmap emphasizes a sequence from Majorana control to hardware-protected qubits to larger multi-qubit systems. Microsoft's story is about betting on topological qubits while also building toward logical qubit and hybrid system progress. Quantinuum continues to stand out for logical qubit milestones, trapped ion quality, and hybrid workflow demonstrations. Its public roadmap points to universal fault-tolerant quantum computing by the end of the decade, and it has highlighted logical qubit progress, as well as operational hybrid workflows with Japan's Riken environment. IonQ continues to push the trapped ion case around fidelity, networking, and long-term scale, including public claims of very high 2-qubit gate fidelity and an aggressive long-term roadmap. Other players, including neutral atom companies, continue to push different scale and architecture stories. Together, these players show that the field is still very much open. There is progress, but there is not yet one universally accepted winner in hardware architecture. The quantum race is still open, with different hardware approaches advancing in different ways. When you hear the latest progress in quantum computing, you should not think only about bigger numbers. The more useful way to think about progress is to ask better questions. Are the qubits better? Are the gates cleaner? Is error correction getting real? Are logical qubits improving? Are hybrid workflows becoming practical? Are algorithms becoming more verifiable? Are there signs that systems can solve meaningful problems better than classical only methods? By that standard, the field really has moved forward. Google has pushed error correction and verifiable algorithm claims. IBM has pushed system integration and fault-tolerant building blocks. Microsoft has pushed topological hardware claims and logical qubit integration. Quantinuum has pushed logical qubits and hybrid application workflows. Real progress in quantum computing means better quality, better protection, and more useful workflows, not just bigger qubit headlines. Even with all this progress, you should stay realistic. Quantum computers are not yet ready to replace ordinary computers for everyday work. The main barriers remain the same: qubit quality, error correction overhead, scaling, stability, cost, and software maturity. A useful large-scale quantum computer will likely require many more high-quality physical qubits to create a smaller number of reliable logical qubits. It will also require smarter compilers, stronger integration with classical computing, and clearer demonstrations of practical advantage in real domains. This means the most likely future is not that quantum replaces classical. It is that quantum joins classical. You should expect hybrid systems, specialized applications, and gradual expansion into fields such as chemistry, materials, and optimization. Quantum computing still needs better qubits, better error correction, and better integration before it becomes broadly useful. So, when you ask how quantum computers are built, the honest answer is this: they are built one fragile layer at a time. First, you choose a physical qubit. Then you build the environment that keeps it alive. Then you add control systems, measurement systems, software, calibration, and error handling. Then you try to scale all of it without losing the quantum behavior that made the system valuable in the first place. That is why building a quantum computer is not one problem. It is many problems stacked on top of each other. And when you ask what the latest progress looks like, the answer is not that the race is over. The answer is that the field is becoming more real. Error correction is getting stronger. Hybrid workflows are becoming operational. Hardware paths are becoming clearer. Logical qubits are getting more attention. And companies are starting to compete not only on qubit count, but on quality, verification, and usefulness. Quantum computing is advancing from promise toward practical engineering, but the hard work is still very much in progress. If this session helped you understand how quantum computers are built and where the latest progress really stands, subscribe to the channel, like the video, and share it with others who want to learn quantum computing in a practical and grounded way. Leave a comment and say which hardware path you think has the strongest future: superconducting, trapped ions, neutral atoms, or topological qubits. Your perspective may help someone else think more clearly about where this technology is going next. Learning together is one of the best ways to make complex quantum topics easier to understand.